Remote Sensing. Lecture 1 Introduction to the course. Introduction 1. For man, the need to know the territory and the environment where he lives, it has always been of vital importance, from the origins, when this information was restricted to a set of indications on paths or routes to get food, up to nowadays in which the information gathered through satellites consists mainly of physical measurements and scientific observations. Platforms able to convey information are in fact essential for future challenges. Introduction 2. The actual possibility of observing the surface of the Earth from above could only be achieved with developments in aerospace technology. At the same time, the results obtained in the fields of photography, optics and electronics have made it possible to extend acquisition capabilities beyond the visible, offering man new tools for observing his environment. These are the electromagnetic radiations, which, according to their frequency, have been classified as cosmic rays, gamma, X-rays, ultraviolet, visible, infrared, microwave and radio, up to direct current for infinite wavelength values. Introduction 3. This type of investigation, called remote sensing, studies reality from particular spectral and radiometric points of view, combining observations related to the dynamics of the observed phenomena and their physical contents, with those relative to their position in space, privileged by other disciplines of the survey. From a strictly historical point of view, we can place the beginning of the remote sensing with the birth and development of the photographic technique that took place in 1838, which, together with the properties of various focal length optics, allowed humans to extend their possibilities of vision, as well to record the observations for the first time in the history of humanity in an objective and permanent way. Introduction 4. The possibility to observe above the Earth's surface in order to have a broader and more synthetic vision of the phenomena has always been considered a must, like the shepherds who, in order to count their sheep, look for a hill near their flock. With the invention of the telescope, 1609, and the discovery of photography, 1838, the human observer acquired, in addition to the possibility of improving his possibilities of observation of the real world, the ability to record permanently and quantitatively the information of visual type. Introduction 5. Remote sensing, for all intents and purposes, was born with technological development following the Second World War and took its decisive start in the 1960s in many different fields, such as optics, electronics and information technology, with the development of new sensors, transmissions, and sciences related to data processing. The capacity to extend visual perception beyond natural limits was eventually granted, extending the possible detection and recording in wider regions of the electromagnetic spectra. The first images of the Earth transmitted by the TIROS I meteorological satellite in 1960 produced an extraordinary effect not only on the scientific community, but also on public opinion, convincing scientists of the great possibilities awarded by space platforms. Geomatics, Geodesy 1. The disciplines of surveying, inevitably linked also to those of representation, have as their common object of study the surface of the Earth. Classically they are geodesy, topography, photogrammetry, remote sensing and cartography. Geodesy is a discipline aiming to study of the shape of the Earth, called in geoid technical term. This study necessarily passes through the precise knowledge of the gravity field and its spatial distribution. It is intimately linked to other surveying sciences such as topography, photogrammetry, remote sensing, and representation, cartography, as well as to astronomy, geophysics, geology, oceanography. Geodesy has very deep roots over time, since thousands of years. The problem of the shape of the Earth, flat, round, spherical, had arisen. The hypothesis of a spherical Earth was already drafted by schools of philosophy in ancient Greece. Geomatics, Geodesy 2. Modern geodesy finds its classical formulation following the work of great French mathematicians of the 18th century, and since then, it has been improved by refining the power of mathematical analysis with the precision of the measurements to reach the current levels of relative precision. Consider that now the Earth can no longer, apart from some idealizations, be considered as a rigid body in uniform rotation, but on the contrary, it is necessary to take into account the relative movements of the clods in which the Earth's crust is divided, the terrestrial tides caused from the attraction of the Moon and the Sun, and of many other phenomena. The advent of GPS, Global Positioning System, techniques, which are based on a constellation of satellites, has greatly accelerated the experimental confirmation of theories, reaching centimetric measurement accuracies at a planetary level. Geomatics, Topography, 1. The topography deals with the methods and tools that allow the determination and the metric representation of points and elements of the physical surface of the Earth. This is a very ancient discipline in human history, since even the ancients took care of this, trying, in various ways, to provide a representation, even if approximate. This was due essentially for economic and strategic reasons, as well as religious. All the human activities that involve works and realizations linked to the territory require the metric representation of the physical surface of the Earth, as well as a clearly legible description. Geomatics, Topography, 2. The product of the topography is generally a metric map on an appropriate scale, or a set of numbers that briefly express, by coordinates, the plano-altimetric position of a large number of details of the terrain, digital terrain. Whether it comes to paper map, both to digital terrain, the purpose of depicting portions of territory in a descriptive or synthetic manner, is achieved. The aims of the topography do not end with the numerical description of a particular feature. Its interests involve the control of the structures, the design of reliefs for large civil engineering works, the measures of areas, volumes, the survey of urban centers, archaeological sites, monuments, etc. Geomatics, Photogrammetry. Photogrammetry, especially aerial photogrammetry, is a modern survey method of the territory that allows the production of metric maps. Like the topography, its non-aerial origins date back to the last century, following the discovery and development of photographic procedures, mainly by Italians, French and Germans. Thus aerial survey was born, based, as indeed the terrestrial photogrammetry, on that part of the analytical and projective geometry in which the perspective properties of the photographs are used for the terrain survey, and in particular, the relations existing between the various ways of representing an 2D or 3D object. This discipline is widely used not only in the detailed survey of the terrain, from the smallest scales, 1:50,000, to the largest, 1:200, but also in the survey of architectural complexes and individual monuments, civil infrastructures, roads, etc. Geomatics, Cartography, 1. The basic problem of cartography is the representation of a curved surface on a plane, a problem of impossible solution unless the addition of some deformations assimilating Earth's shape to the geoid, the ellipsoid, or to the sphere. Mathematics, projective and descriptive geometry, information technology, and many other scientific disciplines support the production of maps. The current trend is to store all information through the use of computers. Hence the increasingly important role of digital cartography and geographical information systems, or GIS, geographic information systems. The representation on a plane of information related to curved surfaces can be done either keeping the angles constant, or the surfaces and distances, but not all parameters simultaneously. From these considerations derive the different types of maps and projections. Geomatics, Cartography, 2. The cartography therefore pursues two specific objectives which are metric and thematic, respectively. Metric cartography has the purpose of representing the territory, keeping the dimensions of the represented features as correct as possible. After the reduction in scale, it is generally symbolic and is carried out starting from geodetic and aerial photogrammetric surveys. Thematic cartography represents the territory by surfaces or themes having uniform characteristics, such as urbanized, vegetation, geology, hydrology, etc. It does not have strictly metric characteristics, even though the representation basis is usually metric, but it must provide a realistic thematic accuracy. For this last reason, the thematic cartography must have a regular updating. Generally, such cartography is produced from aerial or satellite data, using photo interpretation techniques or digital image processing. Remote sensing definitions. 1. Remote sensing is the scientific discipline that allows to acquire qualitative and quantitative data on remote objects placed and on the surrounding environment, on the basis of measurements of electromagnetic energy, emitted, reflected or transmitted, which interacts with the areas of interest. It therefore includes all that set of techniques, tools, and interpretation tools that allow to improve the perceptive abilities of the human eye and brain, providing the observer with information on objects placed at a distance and on the surrounding environment. In general, it can be said that remote sensing allows to perform quantitative remote measurements of physical characteristics linked to surfaces and, with certain boundary conditions, also related to subsurface situations. Remote sensing definitions. 2. Data and extracted information, whether qualitative or quantitative, comes from surfaces generally located far from the observer. Reference is made here to distances that can vary from a few meters, proximal sensing, to thousands of kilometers, remote sensing, as in the extreme case of observations made by geostationary satellites, placed in orbit at a distance of 36,000 kilometers from the Earth's surface. A typical example of remote sensing is man's visual system. The vision of an object in fact involves the acquisition of a series of information, shape, color, size, position, etc., on the object and their analysis and interpretation by part of the brain in order, for example, to recognize it. In remote sensing, the measurable quantity is electromagnetic energy coming from investigated surfaces. Measuring this magnitude means quantifying the alterations that the object imposes on the radiation or its characteristics of intensity, frequency, and polarization. This translates into the physical knowledge of the object studied. Remote sensing definitions. 3. Remote sensing extends man's observation abilities into space, overcoming spectral limitations of his retina, enabling the exploration of the invisible fields of the electromagnetic spectrum. This is granted also in a multi-temporal perspective, in the sense that the data taken continuously since 1972 enclose a historical memory of the surface of our planet. With the possibility of acquiring data from space, from different distances and at different times, a new philosophy of control and investigation is introduced in the study of the territory and related problems, based on the ability to observe phenomena not directly accessible to human experience and indicators of current situations, difficult to identify in any other way. Remote sensing definitions. 4. Normally the study and analysis of a phenomenon or a surface carried out with remote sensing techniques involves 3 distinct phases. 1. Data acquisition, usually by aerial and or satellite platforms. 2. Data processing. 3. Interpretation and use of data. As regards the detection instruments used in this discipline, they can be divided into 2 categories, namely those that provide single measurements, such as radiometers, spectrometers, scatterometers or others, and those that provide images, sets of measurements, such as spectrum converter tubes, fast and slow scanning devices, cameras, thermal imaging cameras. Remote sensing definitions. 5. All acquiring tools are called sensors with a meaning that includes several functions: radiation collection, transduction, control, recording, reproduction, transmission. In a more restrictive sense, on the other hand, the term sensor only indicates the radiation collector device, also called detector. Another distinction that can be made is that between passive and active sensors, passive instruments measure the radiation, whether emitted or reflected, from the investigated surfaces, while the active instruments themselves illuminate the surfaces, then capturing the radiation back. The following figure shows the different possible platforms carrying digital sensors. Remote sensing definitions, 7. The data obtained through remote sensing techniques offer specific characteristics and sometimes have extremely significant, in some cases unique, advantages. Among these: 1. The observer is placed in an unusual condition. The clouds, for example, are seen from above and not from below as usual from Earth's surface, and the territory is fully represented without cartographic codes or symbols, and above all without those political, economic constraints that are the borders between nations or the imbalances technological development between one country and another, even if, sometimes, the obvious signs of these imbalances are directly visible on satellite images, for example, images along the Mexico-United States border. Remote sensing definitions, 8. 2. The synoptic nature of the information allows to cover large portions of the territory in a uniform way. The measurements and observations are consistent with each other, being carried out by the same instrument, and are generally carried out in numerical form, thus facilitating their handling and processing. 3. The speed of access to information allows, in certain conditions, to reach the user in almost real time. 4. The association of multiple data in the field of the electromagnetic spectrum and the repetitiveness of the measurements over time are the basic concepts for multispectral and multitemporal analysis. 5. It should be noticed that there is still no sort of planetary spatial right to date. For now, everyone can do everything outside the atmosphere. Remote sensing definitions, 9. The most important feature of remote sensing is then the possibility to acquire data over the whole Earth's surface, stimulating the speculative curiosity of the scientific community, enabling the possibility to study environment and the territory characteristics. Remote sensing is an investigation methodology that requires a multidisciplinary approach, alongside a basic researcher, physics and modeling, and those for data and image processing, computer and electronic. A large group of skilled users operate in different application domains: engineers, geologists, oceanographers, agronomists, etc. Although remote sensing is a relatively recent discipline, its potential can already be found in various sectors with important application examples, and its official inclusion in environmental analysis methodologies is becoming increasingly frequent. However, it should not be considered as an exhaustive solution to solve difficult or impossible cases, but rather as an enrichment and completion of the other more tested scientific disciplines for the study of the environment. Remote sensing components, 1. A remote sensing system, in which electromagnetic radiation is the bond that holds the different components together, can be schematically described as a whole that involves different essential parts: the source of energy, the interaction with the atmosphere and with the Earth's surface, observation and measurement tools, and eventually data processing and interpretation. Remote sensing components, 2. A. Energy source. The source of electromagnetic radiation can be natural, like the sun that illuminates the Earth or the Earth itself, both because it reflects part of the solar energy, and because it emits, for example, thermal radiation, or it can be artificial, like the light of a flash or microwave signals produced by a radar. The characteristics of the source are one of the fundamental aspects in the chain of remote sensing, also because everything that follows, interaction physics, sensors, analysis and interpretation methods, depends on them. Remote sensing components. 3. B. Interaction with the atmosphere. The electromagnetic radiations, in their journey between source and surface and between surface and sensor, travel through the atmosphere and interact with its constituents, gaseous molecules, suspended particles, and aerosols. Energy characteristic can therefore be modified and distorted. Atmospheric diffusion, or scattering, is one of the classical examples, where the lack of visibility and therefore of the transparency of the air, a phenomenon that we experience directly with our eyes, with variable intensity, in the days of haze or heat, or in presence of fog. Remote sensing components. 4. C. Interaction with the Earth's surface. The quantity and characteristics of the radiation reflected or emitted by the Earth are a function of the energy involved, and the characteristics of the objects, the responses of the different surfaces, are far from univocal, instead constituting a complex universe full of ambiguities and variations that must be carefully examined and studied. Remote sensing components. 5. D. Sensors and detectors. Electromagnetic radiation measuring instruments represent the technological part of the whole system. They range from the simplest as the photographic ones to the more sophisticated optical electronic ones. Each type, according to its characteristics, has a particular field of action and sensitivity if compared to the wide range of electromagnetic radiation spectrum. The simplest example is the human visual system, which perfectly represents the project and the realization of a typical remote sensing instrument. Remote sensing components. 6. E. Data processing and interpretation. The final, and sometimes critical, component of the system is dominated by man and his ability to produce machines and systems capable of processing the massive amount of data that is continuously acquired, and to develop methodologies and interpretative models to extract information from data. In fact, even more frequently, classification softwares try to simulate the mental processes of the photo interpreter and to return the final products of a process with direct readability specifications, and therefore compatible with the perceptual characteristics of man and his needs. Remote sensing applications. 1. In order to meet the needs of end users, there are remote sensing systems that offer a wide range of different operating characteristics both in terms of acquisition temporal frequency and spatial and spectral resolution. They range from low spatial resolution and high repetitiveness data for meteorology to very high resolution data required tactical operations, to others that require tight review times for short periods, in environmental monitoring programs, and that normally require a very high number of spectral bands, in an overall context where the global information on the environment is, in some way, exclusive to remote sensing methodologies. Remote sensing applications. 2. Remote sensing is used for different applications such as environmental control and monitoring, urban expansion, soil degradation, climate change, ozone depletion, deforestation, global warming, desertification, etc. Agriculture, phenological state, crop forecast, soil erosion, etc. Mining and oil exploration, earth structure and geomorphology. Renewable resources, wetlands, soils, forests, oceans, inland waters, hydrogeology. Meteorology, atmosphere dynamics, weather forecast. Thematic maps, land use, civil engineering, landscape units. Military reconnaissance, strategic policy and tactical control.